Business analytics students, I'm sorry that I have to miss class due to a sick day, but I'm recording this video in lieu of the missed class. If you're watching this video, I'm going to walk you through the first lesson for Learning Outcome 5 on forecasting models. So the lesson that we're covering today in lieu of our regular class time will be 5.1 multiple regression. We'll be working within Excel for the majority of the lesson. So most importantly, you will need the Excel file for all of the examples and the PowerPoint file for the theoretical component. Some other reminders in relation to assessments are that applied activity 5 on correlation and regression is still due tonight. That is March the 17th at 11:59 p.m. If you do have questions about it, please still send me an email and I can still answer your emails if you are stuck anywhere on that assessment. Your next assessment won't be due for 2 more weeks until March the 31st, so we'll see each other in person in class again before that assessment is due. Okay, so if you've got those files downloaded, some other things to point out under Learning Outcome 5 is that it will take 2 weeks to work through this learning outcome. Your next assessment will be both on multiple regression and time series models. And in the homework and additional resources section, I do have little mini videos on multiple regression and time series. They show you the same types of things for multiple regression that I'll be showing in this video, but in much shorter format. So they aren't quite as long as the video that we're going to have today. And as I already mentioned, the activity that is covering this material won't be due until March the 31st. So you've got some time to work on that one. So first, what is multiple regression? To really understand multiple regression, we first need to remember what we learned about regular, or what you can also call simple regression from our last class. So just as a really quick reminder, last class we did regression for all of these different pairs of variables. So heating cost versus temperature, heating cost versus attic insulation, and heating cost versus the age of the furnace. If I head over into Excel, I've got that same data here. So I've got my heating costs for 20 different houses. And as a quick example, we did a regression to say, based on the outside temperature, can we predict the heating cost? Because heating cost is what we were trying to predict. That would be the Y variable, and the mean outside temperature is something that we cannot influence. So that is the independent or the X variable. For this specific combination, if I wanted to do a simple regression, we learned that there are multiple ways to do it. You could insert a scatter chart. So when you're making the scatter chart, your X variable does have to be selected first. So I would usually just copy paste my Y variable so that it's on the right side of the X. And then from there, I could insert a scatter chart to help me predict the heating cost in relation to the temperature. As temperature is warm, you can see the heating cost going down. And the first way I could do the regression is just with a simple trend line and then displaying that equation on the chart. Another way we learned is you can use the slope and intercept formulas. The third way that we learned is using the regression tool. And this is the one I want to recap in this video because it is the one that will be important today when we expand from just simple regression to multiple regression. So to use the regression tool, you do have to have the data analysis tool pack installed. Then once you click on it, you'll scroll down to regression. The order of the variables doesn't matter here. I mean, you don't have to copy and paste the Y variable to be on the right because you actually have full power to select which variable is the Y and which variable is the X in any order. So for this one, if I select heating cost first, then I could select the outside temperature. I did select the labels starting in row number 3 where it does say the name of the variables. And for the output range, I'm just going to place it here beside where I wrote simple regression review. There we go. So here was my output, and just as a quick recap, the places that we looked at in this output, the most important ones were our intercept. That's where we cross the y-axis about here, and our slope. These were our two most important values, and they should be the same values that we got when we created the equation of the line on the chart as well. They just probably have slightly more accuracy. Something else you'll notice is on the chart we also had an r squared value. That same r squared value is also displayed here. So we've got these three numbers that we focused on mostly in all of this output. For the interpretations, when I inserted my data, it deleted my labels, but for the intercept and the slope, I can show you how those are interpreted because again, this is going to be very important for what we're learning new today. So it's important to have it fresh in your head. So what the intercept means is it will be the value of y when x is 0. So in this case, remember x is the outside temperature. It's helpful often to make sure you have your charts properly labeled so you know which one is on which axis. So temperature is on the x, cost for heating is on the y. In this case, x is the temperature, so how you would interpret the intercept is when x or temperature is 0, that is the cost to heat your house. So in this case, when temperature is 0 degrees, the cost to heat your house is $123 and about 26 cents. That's the value for the intercept. So the intercept is always interpreted as what is y when x is 0. For the slope, instead of x being 0, it actually is in relation to the change in x. So the slope describes how steep this trend line is. So basically what the slope is saying is when you change the temperature by 1 degree, how much is the cost changing? So in this case, when temperature increases by 1 degree, the cost is decreasing by about $13.89. How did I know it was a decrease? It's because the slope is a negative number. So you'll always interpret the slope as an increase in x by 1 unit. How much does y change? If the slope is a positive number, it means that the y variable is also increasing. If the slope is a negative number, it means it's a decrease. So here, when our temperature is going up, so you can see that here, temperature going up, cost is going down by about $13.89. So that is the important information from last class. Also, the r squared value says that this is a moderate relationship between these two things, between cost and temperature to heat your home. So we know that they are related, so that you should be able to hopefully predict costs based on temperature. And that's simple regression. So last class we did this not only for outside temperature and heating cost, but I gave you a task in class to try it for attic insulation and heating cost and age of furnace and heating cost to see if those variables are also related. So that's where multiple regression comes in. Wouldn't it be good to be able to say, instead of trying to predict the cost to heat your home based on temperature, and then doing it all again to predict cost to heat your home based on attic insulation, then do it all again to predict cost to heat your home based on age of furnace? Wouldn't it be good if we could make a prediction for the heating cost based on all of these three things at the same time? And that's what multiple regression is for. Multiple regression is for using multiple x variables to predict one y variable. So that part is very, very important. Multiple regression means multiple x's to predict one y. So we would want to make all of these x's to be able to still predict our heating costs. How do we do this? So multiple regression still forms a linear equation. The way that it's different is instead of just having an intercept and a slope, every single x you add in gets its own slope. So I have my little person here. I always tell students, think about it as slapping in a slope. You have to slap in a new slope for every single x variable you add. So the equation of a multiple regression line will still have an intercept, but you're not just going to have one x value and one slope now. You can have as many x values and as many slopes as you need. So you can just keep adding in slopes for however many. For example, if you had 5x variables, you'd have 5 slopes and 5x's. If you had 3x variables, you'd have 3 slopes and 3x's. The k here just means it can be any number you need to use for your data set. The slope and the intercepts are still interpreted in the same way, more or less. The intercept is still the y value, but when all x's are equal to 0 instead of just 1. So that part's important, that it has to be every x equal to 0. And the slope will be the change specifically for that x variable while you are not changing any of the x variables. So you can only change one at a time. We'll look at those interpretations in more detail as we do an example. What's great about fitting multiple regression is you can use the exact same tool that we used before. Just instead of selecting one x variable, you can select multiple columns to be your multiple x variables. The one thing you have to be careful of is that the columns do have to be next to each other. That's what contiguous means. You can't skip any, so they do have to be touching each other for the x variables. It's okay if the y variable is not touching because that will be in a separate box for entry in the regression tool. So let's try to create our first multiple regression model. I'm going to go back to Excel and we're going to make this model together. So here's where I'm going to put my output for my first multiple regression model. So how it works is in this case, what I want to do is I still want to try to predict heating costs, but what's different than before is instead of taking one x at a time and doing 3 different regressions, I'm going to take all of the numerical values for all of the x's. So again, all the ones that have actual numbers and use all 3 of these to try to predict the heating cost. Again, what we used to have to do 3 simple regressions for, we're going to try to combine into one multiple regression so you can predict the heating cost for a house based on the temperature, the insulation, and the age of the furnace all at once. So if I go to my data analysis tool pack and the regression tool, first for the Y range, it did not change. It's still B3 to B23, which is the heating cost. The X range is what we're going to have to change because now I want to select the 3 numerical independent variables. So these are the 3 variables we're trying to use to predict heating cost. Notice that they are all touching. I didn't skip any columns. That is required. I did select the labels for the variable names, so I've got to check that box. And for the output range, this time I'm going to place it over here under where it says multiple regression, all quantitative. So that should be M3 as long as you didn't insert any columns or change the order of the data, and I'll press OK. Here we go. So here's my output, and it looks very, very similar to what we had for simple regression. So it still has this R squared value that tells you that this is a moderate to strong relationship. If you look at R by itself, not R squared, it is over 0.8. So that would be a pretty strong relationship between these variables. In this section, we have our intercept. I think I was using more of a yellow-orange for that one. We have a slope for temperature, a slope for attic insulation, and a slope for the age of the furnace. So what ends up happening is you get slopes individually for all of the x variables. As I mentioned, think about it like you slap in a slope for each x variable that you have. How do you know which one goes with which? Well, Excel labels them. Mean outside temperature, that's the slope for the temperature. Attic insulation, this one's the slope for attic insulation. Age of furnace, this one's the slope for age of furnace. And finally, our intercept of 140.3187306. We can then interpret these values as well, which we will do in the next example when we have our best possible model. So this is our first ever multiple regression model. it looks very, very similar to our simple regression output, but you will notice changes in the values. So for example, the intercept is not the same number as it was before, and the slope for temperature is not the same number as it was before. And the reason is when you're using multiple variables, it will change the relationship so that they all work together to help you predict the cost to heat your house. So, like I said, it will change the numbers slightly. They won't be the exact same as if you did a simple regression, but you'll interpret them in more or less the same way. One other thing that's really cool about multiple regression is you can also use variables that are categorical. In that last example, you might have noticed me emphasizing that I'm selecting the quantitative or numerical x variables, but it actually is possible to integrate categorical variables as well. In statistics, we can code categorical variables as numbers. So for example, for the simplest type of categorical variable that's just yes or no, we can represent every response that's a yes with the number 1 and every response that's a no with the number 0. We call this a dummy variable. You can think about a dummy variable like a light switch. Basically, when it's a yes, it turns that variable on in the model, like putting on a light switch with the number 1. If it's a no, it like is shutting a light switch off. It's saying that this variable does not have any influence and it's not important. You can do this coding. So to create a dummy variable, when you have text yes and no in an Excel file, you can turn this into a number like 1 and 0 using a simple if statement in Excel. I'll show you how we can do this for the garage variable, which is given in text in the sheet, and then we can try to add the garage into the multiple regression model. Because if you have a garage that's attached to your house and heated, you probably know that it does influence the cost to heat your home. Because if you're heating a garage, it's an extra space that costs extra money. So we want to use the most information possible to try to predict someone's cost to heat their home. And if we don't have like the size of that garage in area, for example, the least I can do is add on some kind of indication on if the house has a garage or not to help me. I removed where I copied that extra heating cost just because I want to make room for the garage variable. So I'm going to move over the garage yes versus no. And I'm going to create a dummy variable for garage. So I'll call it dummy garage using an if statement. So with the if statement, I'm going to say if this is a no, say it's a 0, otherwise it'd be a 1, it'd be a yes. So that worked. It's saying it's a no, so it's a 0. If I fill this down, let's see if it's working for all of them. Yes, 1, no, 0, yes, yes, no. If you see the no's that are 1, this could potentially be a problem with the formatting of data, which you always have to check in real analysis. See how when I click on the no that appeared as a 1, it has a space after it? This is just an error with the creation of the data. So that if you erase the space after the no, then it's coded correctly. So just that one extra space that when somebody was typing in this data, and I took this data from an online source for open data. So when they were typing it in, they must have just added an extra space after some of the no's that's causing this error. So we just want to double check that they're all correct, that there's no extra spaces, because Excel is testing if it's a no with no spaces afterwards. And if it has not that exact match, if it's not no, with no single space after, it will call it a 1 instead of a 0. Excel isn't smart enough just to recognize that the word is the same and the space was the issue unless you specifically tell it to do like an approximate match instead of an exact match. So you would have to manually go in and just erase the spaces like I did for all the ones that are wrong. So now that I've done that and I've erased the spaces for all the ones that had that extra space on the end so that all the no's are 0 and all the yeses are 1s. Now I can try to make a multiple regression model that helps me to predict the heating cost, not just based on 3 x's, but now I can use 4 x's. In Excel, the regression tool cannot use text like yes and no, but it can use the zeros and the ones that represent the yeses and nos to incorporate a fourth variable. By incorporating the fourth variable, I'm now using outside temperature, attic insulation, age of furnace, and the garage to help me predict the heating cost. Let's do that. So I'll go back to my regression tool. My heating cost is still in the input. For the x's, I have to now select all the way from mean outside temperature to the dummy garage variable. The reason I moved the other garage variable over is so that the variables would be beside each other. Remember, when you're selecting with the regression tool, the columns can't skip any spaces. They have to be all in a row, which is called contiguous. So that's why I moved the yes-no garage over one, so that mean outside temperature, attic insulation, age of furnace, and dummy garage would all be touching each other. Then I'm going to place this here in M26. And I now have, again, very, very similar output. The R square was 0.733. This R squared is 0.776, so just a little bit higher, so a bit closer, a bit stronger. The intercept value here is still my Y when all the X's are 0. The mean outside temperature slope, still there. Attic insulation slope, I think I had in green, still there. Age of the furnace was in gray. And I now have one additional slope that I didn't have before for the garage dummy variable. Notice that again, the value of the intercept changed a bit, the value of the slopes changed a bit. Like I said, the same as when we did simple regression, every time you add a new variable in, it does change the relationship between the variables, so that changes the numbers, and it's going to change the predictions for the cost to heat your home as well, based on introducing more variables. So now we have two different multiple regression models. One that has just the numerical values, temperature, insulation, furnace, and this second model we just created that added a variable for the dummy variable for garage. Dummy just means yes versus no, that I took that yes, no, and converted it into ones and zeros so that I can see if having a garage also influences the cost to heat your home. So the next step is, which one of these models is actually better? So is this one better or this one better? Which one do we use? How do we know? Is the simple regression model better? How do we know which one to pick? So that is our next step of this lesson. Which one do we pick? So there's a couple ways and a couple of considerations that you need to look at in the output to decide which one is the best. How the process works is first you make the biggest model possible. So that's always step number one. You make the biggest model possible. For our question, oh, sorry, that's the wrong one. For our question, the biggest model possible would be that to predict why you use outside temperature, attic insulation, age of furnace, and a dummy variable for the garage. Those are all of the possible variables that we are given, so that is the biggest model possible. We fit that model, it is right down here. Once you have your biggest possible model, you go on to the next step, which is to look at the p-values for each of the x variables. So that is found here under the p-value section, and you're looking to see if these p-values are significant or not. This is technically a t-test like we did earlier in the course when we were on the inference chapter. And when we did our t-test, we were always looking if the value was bigger than 5% or less than 5%. Remember, we wanted p to be less than 5% to be significant, and the same rule is true here. We're looking for anything less than 5%. So this one, less than 5%, it means it's good to keep in the model. This one, less than 5% is all good. Attic insulation here is greater than 5%, so that one might be questionable. Age of furnace is just slightly less than 5%, so that one should be good. And finally, the dummy variable for the garage is definitely bigger than 5%. So there are some variables with p-values bigger than 5%. So when that happens, what the p-value being bigger than 5% means here is that that variable might not be good to include in the model. For our t-tests for hypothesis testing, when you had a p-value bigger than 5%, that was a do not reject the null hypothesis. It meant you had to hold on to the null. For a regression, what the null hypothesis means is that the slope isn't really that different from zero. It basically essentially means you don't need to include this variable in your model. Another way of saying that is this variable is not going to help you make a prediction for the y variable. So we have two here that have p-values bigger than 5%, which means that these two variables, attic insulation and the dummy variable for garage, might not be helpful in making a prediction for the cost to heat your home, sorry. So what you do in this case is you do not remove both variables. You remove the one with the biggest p-value only. So we would remove the garage dummy variable only. So you only remove that one variable because it is the worst offender. It's the one with the biggest p-value. So that's step number 3. Remove the variable identified in step 2 from the model that has the largest p-value, but we can only remove one at a time. Even though two variables had p-values bigger than 5%, we only remove the biggest one first. That's because once you remove one, all the numbers will change. The numbers will no longer be the same. Okay, so if I want to find my best model, what I'm going to do is I'm going to now redo the model one more time, but not include the dummy variable I created for garage. So it's going to get me back to the very first model we created. And I'm going to put that over here I'm going to try to find the best model. We'll see if this one is the best in a minute, but for now I'm just trying to find the best. So I redid the model. I got rid of dummy variable for garage because the p-value was bigger than 5%. Now I'm going to look one more time. Are all the p-values less than 5% or any bigger? Intercept, less than 5%. Mean outside temperature, less than 5%. Attic insulation, it is now less than 5%. And age of furnace, less than 5%. So remember, when we included the garage, the attic insulation was bigger than 5%. But when you got rid of garage, it changes all the numbers, so now they are all less than 5%. Once you have a model where all the p-values are less than 5%, that's what significant means, then look at the adjusted r squared. Instead of looking at regular r squared, we look at the one called adjusted r squared because that accounts for adding more variables. In statistics, if you look at how R, the correlation coefficient, is calculated, the more variables you add, it always goes up, but that's an artificial inflation. So statisticians made an adjustment to the formula that they call adjusted R squared that doesn't always get bigger just by adding more numbers. If this is R squared, if we do the square root of that number, this is what R would be. So this is the correlation coefficient, and it is strong. It's greater than 0.8 or 80%. So this is a pretty good regression. What this means is that based on mean outside temperature, attic insulation, and age of furnace, all of those variables have p-values less than 5%. We have a strong correlation. And like I said, once you start getting into multiple regression, you look at the adjusted R squared value instead because it accounts for adding more than one variable to the model. So this is going to be our best model. And once we get the best model, the whole purpose of doing all of this work is to be able to make a prediction based on this model. So I'm just going to color code them so you can see where the numbers are coming from. And we are going to then interpret what these values mean and make a prediction based on the values. So first, the intercept value of 140. It means that the cost to heat your home is $140 and about 32 cents. Before it was when the temperature was zero. But now because we have multiple variables, that is when temp is zero, attic insulation is zero, so you don't have any attic insulation, and age of furnace is zero, or it's brand new. So technically, what the interpretation means here is it's still the cost to heat your home, but it's now when all the x's are zero, not just one of them, all of them have to be zero. For mean outside temperature, again, we always interpret the slopes in relation to the change. So when temp increases 1 degree, cost to heat decreases, again, it's a decrease because it's negative, by $12.32. And I have to add when all other variables held constant. The reason I have to add that is if we're saying that a 1 degree change in temperature causes the cost of heat to change by 1232, you can't also change attic insulation and the age of the furnace at the same time because that would also impact the cost. So you can only talk about changing one at a time to be able to interpret it. For attic insulation, it would be the number next to attic insulation is your slope. So what this means is when insulation increases by 1 centimeter, it's in centimeters instead of degrees, but it's still an increase of 1. The cost to heat, again, it decreases because it's a negative by $4.10. That makes sense because if you add more insulation, you should save money or it should be cheaper to heat your home. And again, we say when all other variables held constant because you're only allowed to change one at a time. And finally, for the age of the furnace, when age of furnace increases by 1 year, because age is measured in years, the cost to heat, this time it increases because it's a positive number by about $8.53 when all other variables held constant. So that's how you interpret when you have multiple slopes. The slopes still mean for a 1 unit change in x, how much does the y, in this case the cost to heat your home, change? But you have to add the stipulation that all other variables need to be held constant. Once you have an understanding of what the interpretation of the slope and the intercept are, we need to use the slope and the intercept to make a prediction. The whole point of performing a multiple regression is to make a prediction. So just to get us to that same place in the slides, here we have the model where garage was not significant. Then we remove it because the p-value is too high. We found that once you remove the garage, all the rest of the p-values are significant. Also, the adjusted R squared showed that it's a pretty strong model overall. Oh, whoops. So now we can finally use it to make a prediction. So in your Excel file, you'll see that I've chosen some numbers for temperature, insulation, and age of furnace that we can use to predict the cost of heat. So let's say that in a month, the average temperature outside is -2 degrees. I have 11 centimeters of insulation in my attic, and the age of my furnace is 4 years old. I can use these numbers to make a prediction for the cost to heat. Remember, the equation for regression is slope times value plus intercept. That's what it was for simple regression. Slope times value plus intercept. The same thing is true for multiple regression, but now you have multiple slopes and multiple values that also have to be added in. Think about just slapping in more slopes every time you add one in. So how we implement that in Excel is it would be, you'd still start with the intercept plus the slope for temperature times what the temperature actually is. But you can't stop there. You have to keep slapping in slopes. So plus the slope for the insulation, what the insulation actually is, plus the age of the furnace slope times what the age of the furnace actually is. So every time you add in a slope, you still have to multiply that by the value, and you would keep adding for however many slopes you have. When you finally press enter, that would be your prediction for the cost to heat this specific house when the temperature that month on average was -2, the insulation was 11, and the age of the furnace is 4. The good thing about using Excel is you can then update this. So let's say that last month, the average temperature was -10. Let's say your house only has 5 centimeters of insulation and your furnace is 15 years old. Then the predicted cost to heat your house for the month is going to be $370.88. So it really does allow you to just adjust it based on your own individual parameters for your house and whatever they are, or you can go back to the original values that I had here. So again, to quickly recap what we did here, you can use multiple X values to allow you to predict one single Y. Instead of doing like 3 separate simple regressions like we did last class, they can all be combined into one multiple regression by using multiple X's to predict one Y. You do have to figure out what model is the best for you, because some of the variables, even though they're in your data, they might not actually help you to make a strong prediction for that Y variable. You determine that based on the p-values. You also want to look at the r-squared value overall to tell you if it's a strong relationship, a moderate relationship, or a weak relationship based on the correlation. Once you find your best model, like we did here, you use the best model to interpret each of the slopes and intercepts, and finally make your prediction on what the cost to heat your home would be based off of all of the X variables that are included. So based on what you learned in this video, the last thing I would like you to do that will help you to prepare for your next assignment in the course is to try an example on your own. So for the 2010 Major League Baseball statistics that are found in the try it sheet, I want you to try to find the best fitting model, and then for that best fitting model, interpret the coefficients. So that means the intercept and all of the slopes. I need interpretations. And finally, make a prediction. So I'm going to show you what that looks like in Excel. So here is the Major League Baseball statistics, and this is where you can put models that you create. It will definitely take you a couple of tries. What you want to do is to predict how many games a team wins based on the runs, hits, strikeouts, earned run average, walks, runs batted in, triples, doubles, and home runs. So to help you get started, the first step you need to do is for the regression model, you would say, I want to predict how many games the team wins based on all of these variables. And finally, put the output just somewhere under where it says the best model. There's a lot of variables here, so that doesn't mean they should all be included. Your first step is to go one by one through all of the p-values and find the one that's the highest. The one that's the highest has to be removed first. You can only remove one at a time. You'll notice that there's lots of p-values here that are bigger than 5%, but you only remove one at a time, starting at the highest. So you'll keep fitting, keep fitting. What I mean by fitting is you'll delete that variable. Like, let's say this one's the highest. You need to delete it. When I say delete it, if you then try to say, oh, I don't want to include runs batted in, RBIs, because it's the highest p-value, if you go into regression, remember, the x values all have to be beside each other without skipping. So it won't let you just skip over runs batted in. You'd have to actually like delete that whole column if you don't want to include that variable. Do the regression again, and you'll keep doing the regression again and again and again until the p-values are all less than 5%. Also, look carefully for scientific notation. If it says E -6, that is a very, very small value. It is not greater than 5%. It's very small. Once you find your best fitting model, you'll have to do a lot of different tries, so I didn't know how much space it would take you. So instead of putting the prediction underneath, I put the prediction here. So you'd actually do your prediction in this slot in the red. So to predict wins, you'd have to do like, this is the number of runs times the slope for runs, plus this is the number of hits times the slope for hits. But you would do that with your best fitting model only. You don't have to do that with every single model. So to recap, what I want you to do on your own, give this a try. It can actually be kind of fun, like a little puzzle to find the best possible model. You start with all the variables like I showed here. Then you delete p-values that are the highest, one by one, until all your p-values are less than 5%. At that point, look at the adjusted R-squared. Is it strong? Is it moderate? Is it weak? That will tell you if it's a good relationship. Once you find that, interpret the slope and the intercepts that are still included, and finally make your prediction out of the numbers that are given here. I will upload the solution after class, but I'll also show you it now. So work on this first, pause the video here, and once you have an answer, now I'm going to show you the solution. So pause it and come back to see the solution. So once you have done your work to find the best fitting model, I can show you which one will be the best. So if you fit all the variables, so all the ones in this data set, a lot of them need to be deleted because the p-values are not less than 5%. You'll have to keep deleting until you're left with only runs, strikeouts, and earned run average. I pasted the data below so I could still have a copy of my original. So here was the data. For only those variables, runs, strikes, and earned run average are the only things that help you to predict if they won according to this statistical model. For those three variables, I interpreted the intercept, the runs, the strikeouts, and the earned run average. Check that your interpretations mean the same thing as mine. They don't have to be written in the exact same order, but check that you have that same meaning. And finally, I made a prediction that I took the intercept plus slope times value for the runs, slope times value for the strikeouts, slope times value for the earned run average to get me my final predicted value. So this one does take a bit of time. Like I said, it's kind of like a little puzzle trying to solve it. So if you got stuck anywhere and have questions for me, please let me know, and I'm happy to talk to you about it in our next class. This is technically the last example for the video lesson today, but a couple of things I wanted to note is I'm going to post the completed version that I filled in with you in this video so that you can reference it to make sure you're getting the correct numbers. And also a quick reminder about assessments is that correlation and regression is still due tonight. That is March the 17th at 11:59 p.m. And your next activity then won't be due for 2 more weeks after that on March the 31st. It will cover the material from both this lesson today in the video, as well as next lesson that we'll be back in class for on time series models. So thank you so much for watching this video. If you do have any questions, please reach out over email, and I look forward to seeing you back in class next week. Thanks, everybody. Bye.